Hi girls, nice talking to you after such a long time. So we'll start our series on Scilab practicals on statistical mechanics. This is the first one, and based on your response, we'll have more lectures. So the question for today is plot the Fermi-Dirac distribution law, or if I can reword it, and then it says plot the distribution function as a function of energy and temperature for an FD system. Now, FD system stands for Fermi-Dirac system. That means a system which governs the behavior of fermions. And you must have studied in your theory classes that fermions are nothing but particles which have half-integral spin, antisymmetric wave functions, and they obey the Pauli's exclusion principle. Okay, so to begin with, I will first define what is the occupation number. Occupation number simply means total number of particles divided by total number of quantum states. And when I put something like this over here, that means n, and then I have this expression for average, and I write FD, then that stands for the mean occupation number. That means mean means actually the total number of particles divided by total number of states, and occupation number means the number of particles in a particular quantum state. Alright, so we are talking about the mean occupation number, and it is defined as 1 by e to the power epsilon minus mu divided by kt plus 1. This is equation number 1, and this plus 1 is very significant because it has a special meaning where Fermi-Dirac statistics is concerned. If this goes or it is replaced, then the system changes. So I rearrange equation 1 and I write it like this. I take out mu by kt outside the bracket, and it reads e to the power mu by kt epsilon minus mu, my epsilon divided by mu minus 1, and then the whole thing there is a plus 1. So equation 1 is rewritten as equation 2, and now I put epsilon by mu equal to z. At this point, I would like you to note that epsilon has the units of energy, and so does the chemical potential. That means epsilon and mu have the same units, so this becomes a pure number. So we are going to use a pure number. This has a lot of advantages. Equation 2 then becomes n. I have removed the FD because now it is obvious we are dealing with a Fermi-Dirac system, and I've also removed this mean value, and I've just written n, although this still stands for mean occupation number, but I'll be using this n later on, so I have replaced it, and then this can be written, equation 2 can be written as e to the power mu by kt z minus 1 plus 1. Okay, in fact there should be a bracket over here, and I'm putting it just now over here. Okay, so alright, now for a given value of mu, that means chemical potential, as temperature increases, mu by kt decreases. Right? Now I take the extreme case where mu by kt is equal to 1. So 3 becomes simply n is equal to 1 by e to the power z minus 1 plus 1. Okay, in all these cases there is a bracket over here also. I'll just put it over there, or just to pause. So starting from here again, I have n is equal to 1 by e to the power z minus 1 plus 1. Right, this is equation 4. Now, before I go on to the computer programming, I would also like you to have a look at the graphs, that expected graph that I have drawn over here. So if I plot on the x-axis e by u, I've written e by u because in the programming it's difficult to write the Greek letters like epsilon and mu, so I've replaced epsilon by e and mu by u. So this is simply e by mu, which is equal to z, and on this side we have n. And then you might have seen in your theory classes that for t is equal to 0k, that means absolute zero, the mean occupation number for all energy levels below mu, below the chemical potential, becomes 1. That means all the states are occupied. And all the energy states for energy values greater than U are all empty. The occupation number is 0. So all filled, all empty. So this is just a rectangular shaped curve over here. Right? Now as you go on increasing the temperature, the graph becomes winding like a river. So if I increase from T to T1, this is the red dotted graph. It goes like this. All right. And then you have the, if I go on increasing to T2, actually this T2 should have been here, then we get this black graph. And again, if T3, if we increase that to T3, then we get a graph even more, more inclined to this, and so on and so forth. That means the further you move from T is equal to 0 or greater the value of the temperature, the graph moves away and becomes more and more winding. So this is the graph or the Fermi-Dirac distribution law that we should be able to draw with the help of Scilab. Right? So we begin with the sign notes. You go to the sign notes, and the other details we'll see on the computer screen. But as you have learned how to define a function, we'll define function n. This stands for this n, and I'll write a function Fermi1. This one I have just this I choose because it's a Fermi-Dirac statistics, and I write 1 over here because I have taken mu by kt equal to 1. So Fermi1, and you can see that the only variable on this side is z. So I write Fermi1 as a function of z, semicolon, for reasons that you already know. And I write this expression n is equal to exponential z minus 1 and plus 1 to the power minus 1. I think you will understand that from 4 we can write this straight away. And then of course n function, as you learnt in the earlier classes. And I allow z to take the values from 0 to 0.01 up till 2 in intervals of 0.01 up till 2. We define another function n, but this time I write Fermi2 because in this case I'm going to take mu by kt is equal to 2. So n becomes exponential twice, and this is the asterisk signifying multiplication, z minus 1 plus 1, same as here, and to the power minus 1, n function. And so on and so forth. I can go on increasing the values of mu by kt and plot many such functions and name them as Fermi1 to Fermi5. And I'll show you that I have done that in the sign notes that I have written, and I can also show you the plotted graph. Now after all this, you write plot z Fermi1, and I write in inverted commas r. That means the graph that you will get will be red in color. Similarly, I write plot z Fermi2 and b, that stands for blue, so the graph will be in blue, and so on and so forth. Now after you've done that, you have to write x title, mean occupation number versus E by U for every system at different temperatures. This will give you the title of the graph. You will label the x-axis as you've been taught earlier in the classes. You will also label the y-axis, and in the legend you write Fermi1 and Fermi2. I think this is rubbed off a little, but we can still, you can see that this stands for nothing but Fermi2. That is all. All right. So this is basically the program. I've given you an idea of the program. Now we'll go to the computer screen, and there you can see the exact program that I have written, and you can also see the graphs that that are plotted with the help of that program. If we, taking off from where we left on the whiteboard, the function will read like this. The first line will be func prot theta, as you have always done. This is to protect the function. And then we will have CLF, that means you clear the graphical screen. And then we have a few more lines, and just before the line, on each line, we have put 2 slashes, right inclined slashes, which means that the computer doesn't get the message. Those messages are for you, for the examiner. So in the first line, I write Fermi-Dirac distribution because you're dealing with this. And then I write n is equal to exponential e minus u k into t plus 1 minus 1, which is the formula that we have seen earlier. That means formula number 2. I write the Boltzmann constant in electron volt per Kelvin, and I also take a value of mu. I don't specify the element. I just say that it is 7 eV, electron volt. So you can see that epsilon mu by kT becomes a pure number. From the units itself, we can make that out. And then what follows is what I had already written on the whiteboard. That means function n is equal to Fermi 1z, etc. N function, then z I have taken as 0.01, etc. And then I go up till Fermi 5. Every time I increase the value of mu by kT, it goes from 1, then 2, 10, 100, and 1000. All right? So the higher the value of mu by kT, lower is the temperature. So when the last one, Fermi 5z, where I write Fermi 5z, I have taken mu by kT is equal to 1000. So this is the nearest value to 0. Not exactly 0, but very, very near to the value. A little less is 100, and so on and so forth. And on the whiteboard, I had shown just plot Fermi 1, Fermi 2. Here I have gone up till Fermi 5. So it's just for 5 temperatures. And the rest of the things, as I mentioned before, it is the same: X title, X label, Y label, HL, legend. Legend is what you get on the right hand side of the graph. Now, after having written this, I go to, you can have a look here, I go to save and execute. I do that. I've already done that, in fact, saved and executed. And then you will see the graph that has come. And I'll take it a little further, and you can see the graph that it has come. It is very much similar to the expected graph that I had drawn earlier on the whiteboard. This red line which I have drawn, that is the one which is closest to 0. The black one is a little less than 0, and so on and so forth. And the red one has the highest temperature. So this is how you have to draw the graph. And you can see that you have got the legend on the right hand side of the graph. The X and Y axis are labeled, and there is also a title to the graph. So one thing I would like to tell you over here, that if I change the value of z, that means if instead of 0.01 I take some other value, let us say I just take 0.1. Okay, I've changed it to z is equal to 0. The interval is 0.1 and 2.0, and then of course again I go to save and execute. Then the graph changes slightly, because this gives you the red graph, but it is superimposed on the black dots. So this is not so clear, where in the earlier graph red and black dots had come differently, but here it is overlapping. So by changing the interval, you can get better graphs, and it depends on you. One thing I would like to tell you, you must have studied that in the graphs, all for whatever temperature, when epsilon is equal to mu, that means epsilon by mu is equal to 1, all the graphs will pass through 0.5. That means the mean occupation number has to be 0.5, whatever be the temperature at epsilon equal to mu. If you look at equation 1, if epsilon is equal to mu, then E becomes, the exponential term becomes e to the power 0 by kT. So whatever be the temperature, that becomes equal to 1. So 1 by 1 plus 1, that means it is equal to half, and that is what is represented over here. And for whatever be the temperature, all graphs have to pass through 1. So just try this out. If there are any problems, you can ask me on WhatsApp. and then we can go ahead further. Once you have understood this, plotting similar for Bose-Einstein statistics will be just child's play. Once you do this, there will be no problem. So happy plotting time, and get back to me on your WhatsApp.